You know that feeling like you just can't have it all? Well, it turns out that's not just a feeling. It's a fundamental rule of the universe. Today, we are diving headfirst into one of the weirdest, most mind-bending ideas in all of physics, the uncertainty principle.
I mean, that sounds like a riddle, doesn't it? But here's the crazy part. It's not. This is a real, fundamental law of quantum physics. It puts a hard, non-negotiable limit on what we can ever know. And get this, it's not about our limitations. It's about a limit that's built right into the universe itself.
Okay, so let's get into it. What does this fundamental limit really, truly mean? Let's break it down.
Right off the bat, we have to clear up the single biggest misconception out there. This has nothing to do with having sloppy tools or not being careful enough. The uncertainty principle is not a measurement problem. It is a fundamental, built-in property of nature. I mean, it is literally woven into the very fabric of reality. And this whole thing revolves around something physicists call complementary quantities. The easiest way to think about this is like a cosmic seesaw. Imagine position is on one end and momentum is on the other. The more you pin down one side, let's say you nail the exact position, the other side, momentum, just flies way up into the air, becoming totally fuzzy and unknown. You just can't have both perfectly precise at the same time.
But why? Why does this cosmic seesaw even exist? Well, the answer is somehow even stranger than the question itself. And to get there, we have to totally rethink what we even mean when we say the word particle.
Okay, so you're going to have to forget that old picture of atoms as tiny little solar systems, with electrons as little planets. That's not really how it works. Down at the quantum level, particles, like electrons, act a lot more like waves. Think ripples on a pond. And once you make that mental shift from point to wave, the whole uncertainty thing starts to make a weird kind of sense.
Just think about it in terms of sound. A single pure note, like from a tuning fork, is a nice, long, spread-out wave. You know its frequency perfectly, but where is it exactly? It's kind of everywhere. Now think of a short, sharp clap. That sound is located right here, right now. But what's its frequency? Well, it's a messy jumble of a ton of different frequencies all mashed together. To pinpoint a location, you have to have that messy mix of wavelengths.
And here's the absolute kicker. In quantum mechanics, a particle's momentum is tied directly to its wavelength. So, if you have a really precise position, or short, sharp clap, you must have a messy mix of many wavelengths. And a messy mix of wavelengths means, you guessed it, a messy, uncertain momentum. See, it's not some spooky magic. It's just a fundamental property of how waves behave.
Of course, the great Werner Heisenberg distilled all of this into one elegant and, kind of intimidating equation. But don't get hung up on the symbols here. All this equation is really saying is that the uncertainty in position times the uncertainty in momentum can never be zero. They're locked together. If you squeeze one down, making it more certain, the other one has to expand. The universe simply forbids you from knowing both perfectly. And just when you think you've wrapped your head around it, it gets weirder. Because it's not just that these properties are fuzzy on their own. The very act of us trying to look at them actually changes the reality we're trying to measure.
I mean, how do you see anything? You have to bounce light off it, right? A photon hits an object and reflects into your eye. Now, for big things like a baseball, a photon bouncing off it does, well, basically nothing. But for a teeny tiny electron, getting hit with even a single photon of light is like a bowling ball hitting a ping pong ball. The very act of measuring its position completely changes its momentum. You can't just be a passive observer here. You are part of the experiment, and your observation changes the outcome.
Okay, I know what you might be thinking. This is all very weird, abstract quantum stuff, but does it really matter? Oh, it matters. In fact, this isn't just some quirky rule for subatomic particles. It's the fundamental reason you and I and everything else even exist.
So let's get down to it. So why does this fundamental limit actually matter in our world? What does a fuzzy electron have to do with, say, your morning coffee? The answer, it turns out, is everything.
This right here, this is the big one. If the uncertainty principle didn't exist, atoms wouldn't be stable. Think about it. If an electron could have a precise position and zero momentum, it would just fall directly into the nucleus. Poof! Every atom in the universe would collapse. Matter as we know it just wouldn't. This principle is the universe's built-in safety net that keeps everything from falling apart. It's the reason we're here at all.
And it goes way beyond just, existing.
This principle is at the very core of so much of our technology. It's what engineers of electron microscopes have to wrestle with, balancing how clearly they can see something versus how much they disturb it. It's fundamental to spectroscopy, which is how we know what distant stars are made of. And maybe most importantly for us today, it underpins all of semiconductor physics. That means your phone, your computer, every piece of modern electronics works because of the rules set by uncertainty.
All right, let's zoom out. What's the big takeaway from all this for how we see the universe? Well, it basically means we have to take the old, classical rulebook and just toss it out the window. We have to be ready to embrace the reality that is fundamentally stranger and, frankly, a lot more interesting.
Now, uncertainty doesn't mean the universe is just chaotic and random. It's not a cosmic casino where anything goes. What it does mean is that at its very core, the universe is governed by probability. It operates on odds, not on exact clockwork-like trajectories. We can't say for sure exactly where an electron will be, but we can describe the wave of probability of where it could be. And that's a completely different kind of order, isn't it?
So in the end, the uncertainty principle isn't really a story about what we can't know. It's a profound statement about what the universe fundamentally is. It tells us that at the smallest, most basic scales, reality isn't built from solid, predictable little points. Instead, it's woven from these incredible waves of probability and possibilities. It's a shimmering, dynamic, and ever-changing reality. And you have to admit, that's a much more amazing universe to be a part of.